The next talk is a presentation of the paper Elastic Sheet-Defined Functions, Generalizing Spreadsheet Functions to Variable Size Input Arrays, which is about helping end-user spreadsheet programmers to write more flexible functions that work over inputs of arbitrary size. The authors of the paper are Matt McCutcheon, Judith Borchhaus, Andy Gordon, Simon Peyton-Jones, and Advait Sarkar, and Matt will be presenting.
Hi, I'm Matt McCutcheon, and I'm going to talk about a method of automatically generalizing spreadsheet functions to variable size input arrays, which we've nicknamed Elastic Sheet-Defined Functions. The spreadsheet is by far the most widely used functional programming environment because it's so easy to use, even for people unfamiliar with conventional programming. For instance, suppose we're shopping for a set of foods and the prices are given without tax. We want to compute the total amount we'll pay, including the tax. We just type our starting data into the cells and enter the formulas we want to calculate into other cells. If it's too mind-bending to calculate the tax on all the foods at once, we can do it for the apple and then copy the formula. We have to be a little careful with relative and absolute referencing, but if we make a mistake, it's easy to spot and fix. We can work one step at a time and always see all the data at once, so for a simple problem like this, we never have to think very hard. Now suppose we want to total a lot of shopping lists. Of course, rather than make many independent copies of the formulas, we'd like to reuse them so that if we have to fix a bug in the original formulas, the fix takes effect on all the shopping lists. Since we're familiar with calling built-in functions like sum, can we define our own function for the shopping list that we could call? In current mainstream spreadsheet tools we can, but we have to rewrite the logic in a separate programming language such as Visual Basic, which sacrifices all the usability advantages of spreadsheets. Fortunately, there's an easier approach that has appeared in many research systems, and we think it's only a matter of time before it becomes mainstream, the sheet-defined function, or SDF. To make our original formulas into an SDF, we just mark the cells that represent the inputs and output of the function and give it a name. Now we can call shop on the second list just like a built-in function. Semantically, the tool makes a temporary copy of the function body with our new input substituted in and returns the new output, though of course the tool can optimize this process. The user can open the temporary sheet to see what happened. This requires users to think a little harder, but we think many of them will be comfortable defining SDFs, and the rest will at least be comfortable calling them. However, we quickly run into a problem if we call shop on a shopping list of a different length than the original. When we try to put the pre-tax prices in the input range, they'll get cut off and we'll get the wrong answer. The result we'd like is as if the body of shop were resized to fit the input. How can we make shop behave this way? One approach is to let the entire array of prices be stored in a single cell. If we apply an operator like plus to two arrays, we're implicitly adding the corresponding elements. This will work regardless of the sizes of the arrays. This is a little more for users to learn, but it's a plausible solution for shop. However, for more complex SDFs, the array programming approach becomes unmanageable. Here's a sheet containing the transaction history for a bank account with interest compounded daily. To compute the balance after a transaction, first we apply the interest to the previous balance based on the number of days since the previous transaction. Then we add the amount of the current transaction. This example presents two new problems for the array programming approach. To line up the previous dates with the current dates, we need to shift the array in A4 down one element and add A3 at the top. Let's assume that a spreadsheet tool designed for array programming will have a shift down function to do that. But for the reference to the previous balance, if we tried to do the same thing, we'd end up with the whole array in C4 depending on itself, which won't work. To handle the iteration, we need to use a special function called vscan2 and pass a lambda function that computes each element from the previous one. Most users won't be able to come up with this unless they find an example on the web that's similar enough that they can adapt it to their problem. If that isn't bad enough, here's another SDF with a naive model of cascading delays in a bus transit system. The idea is that a departure from a station will be delayed if the bus that was supposed to make the trip hasn't arrived yet. We want this SDF to resize in three different ways: the number of time steps in the simulation in the vertical direction, and the numbers of stations and routes, both in the horizontal direction. There's mutual recursion among four of the arrays. While we think this is possible to write using array programming, it's going to be such a mess that I won't even try. So it seems we really do want to resize an SDF at the cell level, effectively generalizing it to handle inputs of variable size. We call the result an elastic SDF. Maybe the user could somehow specify how the resizing should work, but it turns out that for many SDFs, including all three we've seen so far, the user doesn't need to do anything because we can figure out the resizing automatically. That's the topic of our paper. Let's see how the generalization process works in the simpler shop example. For the purpose of describing our work, we use a textual notation for SDFs. Users don't need to know anything about this notation, though we have evidence that some users may find it helpful. Here we have the function name and the input and output ranges. Each line of the body describes a rectangular tile of one or more cells with a copied formula. For example, the first line describes these 3 cells. The given formula is placed in the top left cell and copied to the others with the usual adjustment of relative references. We can now write the elastic SDF that we want in this notation by introducing a length variable alpha that can take any non-negative integer value. Of course, if we set alpha to 3, we get the original SHOP back. We'll call this elastic SDF SHOP1 for reference in this talk, though the user would invoke it using the original name SHOP. When an elastic SDF is called, we set the length variables to match the argument sizes, in this case setting alpha to 6, and substitute them into the definition, giving an ordinary SDF that we can evaluate as before. Note that tiles may collide when they expand. We address this by labeling each reference with the tile or tiles it originally pointed to, and having it read only from those tiles, even if others overlap them. Here, the reference in the sum reads the H7 of tile 4, while the output reference reads the H7 of tile 5. We do this for all SDFs, but to reduce clutter, we won't show the labels for the rest of the talk. The question immediately comes up, is the best generalization of a given SDF always clear? For one thing, we want a generalization that's well-defined, meaning that its references stay in bounds for all values of length variables. For example, if we set the height of the column H tile to alpha, but the height of the column G tile to 3, then when alpha increases, the H tile will be referring to undefined cells below the G tile, so this generalization is not well-defined. From now on, we'll consider only well-defined generalizations. To illustrate the next point, consider this contrived sum2 SDF that sums 2 arrays and adds the totals. Here are 2 well-defined generalizations. Sum2D allows the arrays to be different lengths alpha and beta, while Sum2S requires them to be the same length alpha. We say that Sum2D is more general than a Sum2S, since it can be converted to Sum2S by substituting for the length variables. We prefer Sum2D to make sure we generalize as many degrees of freedom in the original SDF as possible. So given an SDF like SHOP, if there's a well-defined generalization that is more general than all the others, which we call principal, that's the one we want. Unfortunately, there are several problems that can cause there to be no principal generalization. We'll look at one of them. In addition to SHOP1 that we saw earlier, SHOP has 2 other contrived but well-defined generalizations, one that uses only the first 3 items of the input and one that uses only the last 3. None of these generalizations can be converted to any of the others by substituting for alpha, and since they can all give different answers on the same input, it should be intuitively clear there isn't a principal generalization that's more general than all 3. The user probably wants SHOP1, but we have to formalize that somehow. So we introduce the concept of a regular generalization, which satisfies several conditions on top of well-definedness, one of which is that a cell reference can't pick 3 elements out of a larger tile. So SHOP1 is regular and the other 2 generalizations are not. Now, out of all the well-defined generalizations of an SDF, if we keep only the regular generalizations, we can prove that there's always a principal regular generalization, and that's the elastic SDF we use. This can be seen as the analog of the principal type of a term in a functional programming language. Our algorithm to find the principal regular generalization introduces all the variables it could possibly need, generates constraints on them based on the definition of regularity, and then solves the constraints. For example, because of the relative reference between the tiles in columns G and H, we generate a constraint that the heights of those tiles are equal. Again, this is analogous to a type inference algorithm in a functional programming language. We've seen that in order to have a principal generalization, we needed to introduce a concept of regularity that excludes some well-defined generalizations. We try to make it capture user intent, which inevitably involves judgment calls. Our goals, aside from having a principal regular generalization, are to support as many realistic SDF design patterns as we can, and keep the process predictable for users, even if they don't know the detailed rules. Our work represents the first draft of the definition. We expect that future work will refine it. This is all technically elegant, but we need to make sure we're actually making things easier for users. So we did a user study to compare elastic SDFs to the best existing alternative, namely array programming, on a set of tasks based on real-world spreadsheets we previously collected. I'd like to highlight a few findings. First, users experienced lower cognitive workload using elastic SDFs compared to array programming, based on a standard survey called the NASA Task Load Index. Second, we have partial data suggesting that users solve tasks faster on average using elastic SDFs compared to array programming. And finally, while users stated a preference for array programming for simple tasks, they preferred elastic SDFs for more complex tasks. This is no surprise, given that complex tasks are much harder to solve with array programming. These results are really promising, though more work is needed to further optimize the user experience. So, we've seen briefly how we can use ideas from programming language theory to offer spreadsheet users an easier way to reuse logic on inputs of different sizes. You can find the full definitions, algorithms, and proofs in the paper. We look forward to making this functionality widely available to improve user productivity. Thanks for listening, and we look forward to your questions and feedback.
Thanks, Matt. If you're watching the New York stream in Clowder, you should now see a Q&A link where you can ask Matt questions by video chat.